Okay, so let's start. Welcome to our Tuesday seminar. This is actually the last Tuesday seminar of the season. Then we'll start back probably in October. So it's a pleasure to have here today for our talk Anna Maria Gallardo, Jimenez Gallardo. Anna got her PhD in Torino, working with Francesco Massaro on optical and X-ray radio galaxies. Then she spent some time at ISO as a student, and also at CFA in Boston. In Chile, she worked with Eleonora Sani and Chiara Mazzucchelli, still on radio galaxies. Then since last November, she's a postdoc here at DIFA, working with Marisa Bonafede. And she will move soon to Chile for a postdoc fellowship at ISO. September, probably, working still on radio galaxies. And today she will give a talk entitled A Chandra-MUSE View of Feedback in Radio Galaxies. Please, Anna.
Okay, so thank you very much all for coming here. I know it's a summer, so I'm gonna try to keep it short. Please stop me at any point to ask any questions that you would like, clarifications or comments or whatever. So I would like to convince you in this talk of how useful actually high spatial resolution observations in the optical and the X-ray are for studying feedback processes in radio galaxies. So let's start with the introduction. So we study AGN, which are massive galaxies hosting and creating supermassive black holes. And although a lot of us here work on AGN, they're only 10% of all galaxies. So do we just like to study weird objects? Not really. The idea currently is that they're actually a phase in the life of all galaxies. So all galaxies should go to around 10% of their life in the AGN phase. So understanding this phase would give us important clues on galaxy evolution and why the universe looks like it does today. The AGN that I actually focus on are even weirder than AGN in general. So I study radio galaxies that are 10% of all AGN, so a 1% of all galaxies. And these sources are characterized because they have this non-thermal component to their emission that can be seen in the radio, and it's attributed to a relativistic jet. So in these sources, the interaction between the relativistic jet and the environment of the source can be quite important. And this is what I will focus on this talk, and I will refer to as the radio mode feedback. So we actually want to understand this feedback, so the interaction between AGN and its environment, because it tells us something about why the universe looks like it does today. So as you see, this red line is the distribution of mass that we should expect in galaxies. However, what we observe is this blue line here. So we see that there's a deficit. I'm going to focus on the high mass part. So the best scenario that we have proposed so far is that this is actually due to AGN feedback. So the interaction between the AGN and its environment does something that makes stars to stop forming. And this suppression of star formation causes not so massive galaxies to form. That's why you will see so many times AGN feedback everywhere. In particular, although that's the idea is that the more effective feedback is the radiative mode feedback, in which the AGN actually expel the cold gas reservoir that would form stars, the one that's dominating in radio galaxies is the radio mode feedback, in which the radio jet actually heats up the environment surrounding the source and thus avoids this radiative cooling of the atmosphere and the formation of stars. And the radio mode feedback, although maybe it's not as usually as energetic, it's actually the one that shows the best evidences for feedback in AGN, which are these X-ray cavities that have been explained as the radio jets actually inflating buoyant bubbles in the atmosphere and causing these surface brightness depressions in the X-rays. So these are the best pieces of evidence that we have so far of the interaction between the ACN and the radio jets, the intercluster medium and the AGN. So to summarize a little bit, in radio sources, the feedback not only affects star formation by either enhancing it in specific areas or pointing throughout the whole galaxy, but also the interaction between the jets and the ICM can have important effects in the intercluster and intergalactic medium, shaping it, such as with X-ray cavities that we have seen. But the medium can also affect the jets. And we have been proposing for some time already that the radio jets can be shaped by the density of the medium, but also the accretion efficiency of the AGN might be dependent on the medium in which it resides. So, for example, here is a brief overview of some of the morphologies that we can see in the radio, where we can see more disrupted jets, bent jets, also hybrid sources that have like different morphologies at each side, and what's known as FR2s, or like edge-brightened sources, showing these beautiful like well-formed lobes finishing hotspots. And in these cases, the idea is that if a source resides in a richer environment, their jets will be disrupted. While for sources that are in poor environments, the jets are able to develop and grow without problem. And in this intermediate case, for example, the idea is that the source has a different environment on each side. So one side can be disrupted and the other one not. And this is currently the most accepted view of the radio morphology for radio galaxies. Similarly, for the accretion efficiency, we see bimodality in the accretion efficiency of radio galaxies. And we find efficiently accreting sources like the one on the top, so it's a high excitation radio sources or a HER, and low excitation radio sources that are radiatively inefficient. And so far, the consensus has been that low excitation radio sources actually are accreting hotter material and therefore are less efficient in their accretion. And that would be explained by low excitation radio sources inhabiting richer environments, so they're feeding directly from the intracluster medium instead of from a cold gas reservoir. That would be the case for the high excitation sources on the top. So that led to the typical view that we had for powerful radio sources, where sources with FR2 radio morphology, so edge-brightened, would have highly efficiently accreting cores, and therefore they would inhabit galaxy-poor environments, while low excitation road sources would have FR1 type morphologies, so very disrupted, and would inhabit galaxy-rich environments. Nevertheless, this has changed quite a lot in the past years, and we have seen that actually for FR2 sources, the dominant population has low efficient accreting cores. So we still don't understand if this is just a weird subset, but this is the fraction in the local universe. And we don't know why. We don't know if their environments are still maintained or what's the difference, if there's an evolution from one to the other. This is still quite a bit of work in progress. Now, when I refer to the environments of radio sources, I will be referring to the multiphase gas halos in which they are embedded. So these halos are formed by a hot plasma component that's in the X-rays, and that I will talk about the intracluster medium mostly, and then an ionized gas component that can be seen in the optical observations is in the shape of filaments, rotating disks, or plumes, and a cold gas component that I'm not really going to talk about here, but it's seen in the form of molecular clouds and can be seen with ALMA. These multiphase gas halos are actually thought to be very important clues into the AGN feedback and feeding loop for AGN. So they would actually give us an idea on how the accretion of AGN can be maintained, why it could stop, and so far and so forth. So the idea from simulation is that during the feedback phase, we would have the uplift and cooling of gas from the central regions of the galaxy due to either radio jets or outflows. This gas then would cool further and inject some turbulence into the medium. And this turbulence would cause further gas to condense and rain back onto the black hole through a progress similar to a normal rain, feeding again the black hole and reigniting the AGN. And mostly this part right there is what's referred currently as the chaotic cold accretion model. We do have some observational evidence of these multiphase gas halos. So as you can see here, for radio sources, we find in a lot of cases ionized gas features extending up to tens of kiloparsecs and mostly associated with soft X-ray emission. In the literature so far, there have been multiple explanations for the ionization of these sources. So it could be either nuclear photoionization of the IEM, or there could be a contribution from jet-driven shocks, the cooling of the ICM, or of course, a star formation. So we still don't know the degree up to which the jets are collaborating to these extended emission line regions that we see. In galaxy clusters, this phenomenon is even more impressive. So we have seen a lot of systems of filaments in Perseus, for example, H-alpha filaments, which are like radially oriented, kind of chaotic filaments. But also we have seen them more like orderly oriented along the direction of the radio jet in other cool core galaxy clusters, such as this one. And the idea, for example, for Perseus, is that they actually are caused by this chaotic rain onto the black hole. So we expect that to happen in the scales where the cooling time of the gas surrounding is around the same order of time as the turbulent eddy time. So in that range, we would expect to see this chaotic rain, so condensation. And also, the simulations predict and observations have been confirming that these filaments caused by that would have low velocity shifts, but very broad lines, so a lot of turbulence. So in that case, we would say that we are seeing AGN feeding. On the other side, for sources like 3C318.1, we see actually that the filaments are oriented in the same direction of the radio jets, and we see that the corresponding X-ray gas is actually cooler. So in those cases, we associate them with the ICM cooling or to the uplift or cooling of AGN-driven outflows in the same direction of the radio jet. And in those cases, we'd say that we're seeing AGN feedback instead of feeding. Further proof of the connection between the ionized gas and the X-ray gas can be seen from the X-ray cavities. So here you can see a source in which the ionized gas was discovered to be actually surrounding an X-ray cavity. And the idea was that the ionized gas was actually forming an expanding bubble surrounding this cavity and was being either uplifted from the central regions or caused by shock ionization on the borders of the cavity. And the smoking gun for this idea was the presence of these double lines in the optical spectra that mean that we're seeing the blue shifted and red shifted filaments along the line of sight at the same time. So we were decided to look into the whole 3C catalog to see if we found any case where we could also see a similar thing. So another bubble of ionized gas. And in that case, we found this 3C1, which was kind of similar, but not exactly the same. So in the case of 3C1, you can see for the blue contours that the ionized gas actually appears to be spatially associated with the inner part of the X-ray cavity instead of with its borders. That was what has been observed for. So we took a look a little bit deeper into the MUSE observations for this galaxy. And we found a lot of different features that actually deserve in-depth study. So first of all, we see this plume of ionized gas in the northern part of the galaxy. And this plume actually coincides with the position where we have the peak in the X-rays. And it's also expanding after the position of the base of the radio jet. This, together with this characteristic hammerhead shape of the radio lobe and the liner-like ionization state of the ionized gas, make us believe that this is actually a case where we're seeing the interaction between the radio jet and the ICM. And the ionized gas is due to the cooling of the jet-heated ICM. So we have the jet that's heating a denser region of the intercluster medium, and then therefore it's compressing it and cools faster, and we see this plume. So perfect. We already know that 3C186.1 is a good target to study the interaction between ICM and jet. Now, if we look to the filaments, we see first a filament that seems to extend beyond the X-ray cavity. The kinematics of this filament, So the kinematics of this filament are actually consistent with the ones that we would expect for the chaotic cold accretion model. And furthermore, this filament is within the condensation scale that for these galaxies stands between 10 and 50 kiloparsecs. So in principle, this is actually a signature of AGN feeding. so 3C196.1 also could have this fuel re-injected into it that could keep it working. Now, going to the cavity area, that's like the most interesting for us. We saw that actually even separating into velocity channels, we see this ionized gas, especially associated with the X-ray cavity. That can be seen even better, blue and redshift. And mostly if you pay attention to the redshifted filament in 200 kilometers per second, that's the one that we detect with the highest signal to noise, you see that the filament appears to be wrapping along the side of the radio jet and finishing on the base of the radio jet. At even higher velocities, we see this dim arc structure that appears to be wrapping along the base of the jet, also in the inner part of the cavity, and connecting these two filaments. So if you remember, for 3C317, they found this system of filaments that had this characteristic shape, and the concluding was expanding bubble. And if you see here, it's actually kind of reminiscent of that. So we do see this circular shape with these two filaments that could be connected. So is it possible that we're seeing an ionized gas bubble being inflated by the radio jet? In principle, yes. We do find that the jet power would be enough to inflate such a bubble. In that case, we could actually have an indication of the expansion velocity of the bubble and the current power of the current AGN activity that we're seeing. But do we see this overlap of red and blue shifted filaments? Kind of. So we see the overlap, we see the doubling of the lines in the central region of the galaxy. We also see a region where they could be overlapping, where the two filaments could be connecting, but in that region, the signal to noise is quite low. Nevertheless, although we see it quite well in the central region of the galaxy, the way the lines are blended means that with the current spatial and spectral resolution, we cannot distinguish the case of an expanding bubble of ionized gas with the case in which we would have another filament along the line of sight that's being accreted onto the black hole. But we believe that the most likely scenario is actually that we have this ionized gas bubble that's being inflated by the radio jet, mostly because of its morphology and the fact that the power of the jet would be more than enough to cause it. So we cannot really discard projection effects. So the ionized gas could be in principle surrounding the X-ray cavity. But if that was the case, we would be seeing ionized gas where its column density is the lowest. So that would be quite unlikely. And we believe that the most likely scenario is that the ionized gas is actually filling an X-ray cavity, which is the first case that has been ever reported in the literature up to date. In that case, we would have two possibilities. So either it's caused by a different AGN outburst, and in that case, we'll have shock ionization causing this ionized gas. And that is actually consistent with the fact that the cavity age is above 1 order of magnitude, the typical duty cycle of AGN. On the other side, we could have a case similar to 3C318.1, in which we have the uplift or the cooling of warm AGN during outflows. So the filaments that are actually supplying ionized gas, the outer filaments are actually supplying ionized gas to the center, and this gas is being uplifted by the radio jet or an outflow and cooling and causing this ionized gas bubble that we see surrounding the radio jet. So 3C186.1 is actually a very cool case, of study. And we're actually got further Chandra observations to study the central region of the galaxy cluster. And we're requesting for further, higher spatial resolution observations mostly with Eris right now to keep this study going. But after seeing this source, we were actually thinking about studying the rest of the 3C catalog with MUSE and Chandra observations. And we decided to take a look into the distinction between highly accreting sources and lower accreting sources. So the high excitation and low excitation. And so far, we found that the morphologies between the X-ray and the optical are very similar. Now, this was actually found in the past, and most authors have suggested that this could be due to a common origin between the X-ray and the optical emission. and could actually give us some clues of what is the ionization mechanism behind the ionized gas. But so far, that has only been done mostly for the high excitation sources, since the low excitation sources typically have lower luminosities. So we decided to compare optical and X-ray data, and this is a very preliminary results that we got. So we see that in general, for high accretion sources, that are the ones that you see in blue, we find higher O3 fluxes, that's what would be expected, but also lower X-ray fluxes. And while for the low excitation sources, we find an excess of X-rays that could indicate that in general, they're being fed by warmer gas or hotter gas, and therefore they reside in richer environment than the high excitation sources, which is in line with the typical scenario that we have, but that we don't really have concrete proof for right now. Furthermore, it seems that the N2 to H alpha ratio for low excitation sources is actually higher. And that could indicate that they have an extra contribution from shocks that's not present in high excitation sources. So high excitation sources could be more dominated by photoionization from the nuclear, for the idea, while low excitation sources could have photoionization together with the shock ionization. Now, I know that a lot of people have found this like trend between the O3 and the X-ray for quasars, but and some authors before found it with HST data for radio galaxies, but I haven't seen any model that actually predicts that. So if anybody knows of any model, I would be more than happy to know about it and to include it in the paper, because like I haven't been able to find any theoretical thing. So just to summarize, I would say that radio jets are quite important, even if they're rare, and they do strongly impact the multiphase dust halos in which radio galaxies reside. And that 3C186.1 is a perfect example, being potentially the first reported case of an ionized gas filling an X-ray cavity, and also showing signatures of jet ICM interactions, AGN feeding, and AGN feedback. Now, our Chandra-MUSE comparison, although preliminary, actually supports the Herc-Gallardo dichotomy being due to different accretion fuel and also to different environments. However, this still raises the question of the FR2 layered sources, since if FR2 sources have these radio morphologies because they're isolated, that doesn't quite match the low accretion rates. So there's still quite a bit of a problem in the radio source environment topic. So I'll leave it here. Thank you very much.
Questions? One from
coming back to the warm gas in the cavity,
Yes.
and maybe I missed it, but the warm gas seems more extended in the other direction.
Yes.
So you have an explanation for that too?
So for the one on the top?
Yeah.
Yes, so this one is the plume, and we believe that this was seen also in the HST observations. Federica Ricci was commenting a little bit about that too on the paper, but this is basic. Our explanation is that the gas is denser in that region, or we're seeing it along the line of sight. So the jets are shocking the gas, and that's why the radio shape is deformed, and we have this condensation that causes the gas to cool faster.
And you have other, I mean, I couldn't make sense of the kinematics of the warm gas. I mean, you see some sign of rotation for the cold gas, or?
So not a lot. So right now the observations that we have are very, very shallow. So it's a little bit tricky, but there was a little bit of, so the part that's closer to the radio jet is actually more blue shifted than the rest of the filament. So if you see here at lower velocities, the filament kind of starts there. That's it.
So there is no smooth gradient?
No, no. But we're hoping to get more observations to actually do nicer like velocity maps.
More questions?
In the last plot that you showed, we're talking about the flux.
Yes.
It was the right?
Yes.
And fluxes are like the intrinsic charge, or like, because maybe you will have like a different sample of the age, right? Like
So for the X-ray flux, we corrected for the galactic NH, but not the intrinsic NH. The things like previous works of the Chandra catalog kind of said like, oh, it's fine. It's not really that different between the 3C sources. The problem we cannot really do with most of the sources, we cannot really do spectral analysis because they're snapshot observations. So most of the X-ray catalog for the 3C are 8 kilosecond on the X-rays.
So maybe you can use the Harm's ratio to get a rough estimation.
So that's another check. So for example, we want to check all that. We want to check the O3, like the extension, things like that. So, yes.
So a possibility could be to compare your emission line ratios in the optical with the photoionization shock models. There are some computation. I remember those from the optical Curie. Did you plan that could tell you something about if it is a shock or ionization from
Yes.
luminous source, formation or whatever?
Yes, that's part of the plan.
You can do that.
Yes.
Okay. Any other question? Online? Is there any? Yeah. Franco, please go ahead.
Hi, I wanted to understand a bit more. So you really mean there is a chance that there is ionized gas that entered from the surrounding medium into the cavity region?
Not from the surrounding, but from the central region of the cluster or the galaxy. So
Sorry,
it's like so not for the surrounding, but from the central region. So actually the gas, like if there's another episode of agent activity being uplifted from the central region of the cavity of the source to the cavity.
Okay, so it's
Sorry, we lost you. Yeah.
okay, thanks. Bad connection, but
Yeah.
I heard the answer. Thanks.
Any more questions from the public or from online? If not, let's start again, Hannah. And and see you October, September. Next year. Not that far. Thank you very much.
Thank you.
Wow.
Ciao.
Ciao.